Hi everyone! How are you all? Are you doing well? Oh my gosh, I miss your little faces. I hope you're all doing well. So here's some FRQ practice things. Some of them are from AP, some of them are from other sources. It's exciting stuff. This is the wrong order. Oh, I gave you it in a different order, but that's okay. So we're doing a new thing today. Now, instead of putting them in a Google Doc, which is eating up my storage, so I can't do that anymore, I am now going to be the latest, what do you call it, YouTube star. Huh? Are you going to give me hits? You're going to I don't know, how do people make money with YouTube? Are you going to make me famous? Oh, yeah. Anyway, so have you been watching those videos? This is my comment. They didn't ask me to do one. Why did they ask me to do one? I think I'm more entertaining than these people have been. I don't know. They were both really good. I'm not. They're doing a good job. Anyhow, free response questions. How are we doing with these? Explain each of the following. I'm going to do it on here. I don't have enough room, but I'm going to do it on here. So I'm going to do A up here because I want to just do it here. Alright, first ionization energy for magnesium is greater than the first ionization energy for calcium. Here we go. Here's magnesium, here's calcium. Alright, so why would it be greater for magnesium than it would be for calcium? And so I said the first IE of calcium is less. Because it takes less energy, so you kind of have to identify what ionization energy is, right? You have to identify that in your answer. If you're watching the videos, they talk about how your answer really has to answer the question. So the first ionization energy is less because it takes less energy to remove an electron. Actually, I'm kind of doing it backwards, but I think it's still okay. I should probably do it the other way. So the first ionization of magnesium is more because it takes, and if we're going to answer the question, we should answer the question, more energy to remove an electron. So why is that? Magnesium has fewer energy shells. And less shielding. So its nucleus has a stronger pull on the valence electrons than calcium's does. I think that's a good answer. Alright. The first and second ionization energy for calcium are comparable, but the third ionization energy is much greater. We need to explain that. Alright. So calcium has 2 valence electrons in its outer shell. And since it is a metal, they are not held tightly. And can be removed relatively easily. Let's use good English, or proper English. But after, I'm being wordy here, after the second electron is removed, the calcium ion has a stable noble gas configuration. Eight in the S&P. So it takes significantly, can you see all this? More to remove the third electron. What is that sound? Oh my gosh. My crazy neighbor is cutting down all the tree branches off his tree. Because he does that every year, and his wife looks at him and says, "What?" Anyway. Alright. There are 3 peaks. Let's look at C. There are 3 peaks of equal height in the PES of carbon, but on PES of oxygen, the last peak is twice as high as the others. Alright, we need to explain that. So you really should. Here's carbon, because the PES reflects the electron configuration. And that's carbon, and that's oxygen. Oops, that should be a P. 2P4. Alright, so there are 3 peaks, twice as high as all the others. Why is that? And that is because in the 2p orbital of oxygen, there are twice as many electrons as any of the other orbitals. Whew, this is great! Alright, where am I going to put D? I don't have room for this. Well, this was C. Here I'll put D. Alright, the first ionization for aluminum is lower than the first ionization energy for magnesium. Alright, let's do this again. 1s2, 2s2, 2p6, 3s2. And then that's magnesium. And then aluminum, 1s2, 2s2, 2p6, 3. I don't have enough room. Let's do it here. 1s2, 2s2, 2p6, 3s2, 3p1. So, why would it be easier? I mean, think common sense wise. Like, why would it be easier? Take less energy to remove that electron than that one. Okay, so I'm thinking the electron in Mg is in a full sublevel or orbital. Whereas the one electron in what is this? In the 3p for aluminum, whereas we'll say there is one electron in the 3p for 3p, which holds 6. When full in aluminum, so it's easier to take that one electron. Oops. Oh, this is so fun. All right. Above mass. Oh, that should say mass. Spectra for the hypochlorite ion. And oxygen has only one stable isotope, which has 16 AMU. So how many neutrons does the most common isotope of chlorine have? Well, this is chlorine and oxygen. Oxygen only has one. So if we take 51 minus 16, that's going to be the most common isotope for chlorine. It's going to have 35 neutrons, because this is the yeah, it's going to have 35. Well, wait, is that right? That's the mass number. Hold on, anything a second. Okay, so yeah, this is the mass number of the most common isotope of chlorine, but it says how many neutrons does it have. So this is the mass number. You then need to subtract the number of protons, and that would give you the number of neutrons. So that is the answer to A. Let's do B. Using the spectra, calculate the average mass. Okay, so this one, normally they give you the percentages over here. And they didn't here, so this is what you have to think. So we start with 100%, and this is like the percentages. So if you have 100%, and this is clearly like 3 times the size of this, so if you think about that, 100 is going to equal 3x plus x. What is x going to be? X is going to equal 25. So this one is 25%. This one is 75%. All right, so we are going to take 0.75 times 51, and I'm going to get, and you don't, this is, these are added numbers. Atomic mass units are protons plus neutrons, so it's not a measurement. And these are percentages, which are not necessarily measurements either. So we're just not going to do sig figs. We're just going to add them together. So it's 51.5 atomic mass units. What? Right. C. Does the negative charge on the ion affect a mass spectrum? No. Because electrons, there's a lot of noise going on in my house right now. I got my son upstairs stomping, I got my husband down there on a business call being loud, and I got the neighbor out there cutting down all his trees. Good heavens. I should go shut the door because he's loud. You want to hear my husband? I'm going to pause. I'm going to go shut the door. Okay, I'm back. Alright, where was I? Because electrons have insignificant mass. So they don't affect the numbers. Remember, this is mass number, which is protons plus neutrons. The electrons have no thing. Alright, the negative charge is on the oxygen. Why? why do we always put, if you have two things and one's going to be positive and one's going to be negative, which one's the one that's more negative? The oxygen is more electronegative. What? This is so fun. Think of this. We're going to get fives. Alright. Now, like, you... should I go this way? Okay. This is what you have next. I just put it in the wrong order. Alright. The average atomic mass of naturally occurring neon is 20.18. And there are two common isotopes right there. So using the information above, calculate the percent abundance of each isotope. Alright, so we know what the average is. And the average is equal to, focus again. The average is equal to the percentage times the AMU. So we know what, and so you take it's a weighted average. You take the percentage times the AMU of one, and you add it to the percentage times the AMU of the other. We don't know what the percentages are, but we know that the two together are going to make 100%. So when I did this, I said, okay, this is going to be 1, which is 100%, minus x, because when you're taking the percentages, you like move the decimal point to the left. So instead of saying 100, I've moved the decimal point to the left. So that is going to be 19.99 plus x times 21.99. So what I'm thinking is, you know, if this one is x, this one's got to be 100 minus x. So, and because we use, when we do the multiplication, we're using percentages, so we move the decimal point 2 places to the left. I just started, and that would give us easier math anyway. So when you do that math, you get 20. Algebra. Do you like doing algebra? We get 19.99 minus 19.99 plus, oops, x, 21.99x. So then that is equal to 0.19. You guys subtract that, and then you're going to add those together. Is going to equal 2x. So x is equal to 0.095. So the percentage of this is going to be 0.095. And 1 minus 0.095, the percentage of this is going to be 0.905. Oh, so, well, the percentage then is 90.5% neon and 9.5%, neon 20 and 9.5% neon 22. Okay. That was interesting. Can you like practice your algebra skills? I'm going to have to stop this video soon. Alright, a major line in the neon spectrum has this for its frequency. Ooh, calculate the wavelength. Look at that. In nanometers. I think, well, I don't know. You're going to get this thing on your computer, but you can highlight with, well, I don't know. You don't want to spend too much time because you only have 45 minutes. But I like to highlight. You got to pay attention to the details while you're doing this thing. Alright, so that's our frequency. Calculate the wavelength in nanometers. So you do have, where is it? You have this. Gives you the equations, gives you the numbers. Okay, but remember, speed of light. What are we looking at? Yeah, speed of light. That unit there is meter. It's not nanometer. It's meter. So speed of light, which is 2.998 times 10 to the 8th is going to equal, what are we trying to get? Wavelength times frequency. We're given the frequency. And then when we solve for x, oh wait, I didn't do that. Well, I'll go back and do that in a second. Ah, look at me, I'm crazy. Alright, so that is equal to 6.91 times 10 to the negative 7th meters. But it wants nanometers. So nanometers, that's 1 times 10 to the 9th nanometers per meter. Nano. So that is going to equal 6.9. This is equal to 690. That's exciting. All right. We forgot to do this. Calculate the number of atoms. Did you see that? Calculate the number of atoms in a 12.55 gram sample of neon. Alright, so naturally occurring N22. So we have N22 is 0.095, right? Alright, so 0.095 times 12.55 grams of neon. Alright, and now it says atoms. Oops, that should be neon. Alright, when we have grams and we want to get to atoms, we've got to use molar mass. Molar mass in neon is 20.18. And then atoms, and I'm ready. So the thing says 6.022. I'm used to doing 6.02, but I don't know if it makes that much difference. I don't know if you use 6.02. I don't think they'll take off. Atoms in neon per mole in neon. So that is going to equal 3.6 times 10 to the 22 atoms of neon. Alright, I'm going to stop this because my video is getting too long.